Okay, so it's Fourier day number 2. So the plan is to sort of go over the transition from sort of time to space, because when we're talking about images, we're talking about x and y, or x and y and z, as opposed to time. And so there's a couple things. One is the equation is identical, except we substitute in, x for t. But we also have a second and third dimension of either the object or the Fourier domain version of the object. And so we'll sort of gradually introduce that. But before I start with that, I just wanted to just mention a little bit about, so if we go back to our simple representation of a complex number, so of this particular complex number of like e to the I some angle, and this one sort of always is confusing to me. But if you have a positive angle or a negative angle, there's an asymmetry between the sine and the cosine part. So the sine part is the imaginary part. So here's minus I, and here's the real part. So when you take the negative of this, so what's another way of writing this out? Another way of writing this out is the cosine of the angle plus this imaginary unit I, which moves in the in the imaginary axis instead of the real axis, times the sine. So this is kind of the x component and the y component. Now if you take the negative of that, so if we take e to the minus I, that equals e to the I times the minus angle. And so then we should just minus the angle here. But there's an asymmetry, because if you do the cosine of minus the angle, that turns out not to change. So cosine of minus the angle plus I times sine of minus the angle. So it turns out this cosine of minus the angle is the same as cosine of the angle. And why is that? Well, if you plot out cosine, cosine sort of goes like this if this is 0. So that's cos. And if you plot out sine, sine goes like this. There's sine. So if you look at those functions and you go, so you can see in cosine, if you flip it around the y-axis, it looks exactly the same. You can't tell the difference. And what does that mean? That's like taking the negative of it. So if I go out this far and then I just take the negative of that, I get exactly the same thing. So this has no effect. But if I take the negative, if I go out this far and take the negative of it, well, clearly I'm going to get a different thing in the case of the sine. And so what this boils down to is, it's often, since cosine of minus angle is the same as cosine of angle, it just boils down to the cosine of the angle. And so then this thing can come out and you can put this here. So they typically would write this like this. So that's e to the minus I. So when you work through this, you see there's this weird asymmetry. So the sine, if you take the negative of of the argument of a sine, it changes. If you take the negative of the argument of a cosine, it doesn't change. So this one is called an odd function, and this is an even function. So there's this clear asymmetry. So the other thing that I mentioned was about correlations, and so I'll just write it out. So one of the things about decomposing a signal into sines and cosines is that they're all at right angles to each other. All the components are at right angles. It's like a principal components of a signal using principal components that are spread across the whole signal. And so the correlation of the cosine of a particular frequency, and we're now going to multiply by x instead of t, and a cosine and the sine of a particular frequency times x, so that we get an angle. Because remember this is all. This is an angle, but often when we're looking at the Fourier transform, we're looking at e to the minus I 2 pi times frequency times time. This whole mess here is basically an angle. So in order to get an angle out of a frequency, we have to multiply it by space or time. So in the time case, we had like cycles per second times, seconds equals cycles. In the spatial case, which we're going to talk about, we have cycles per image. So cycles per distance times. So it's cycles over x. Times x. That cancels out, and you get cycles. So we'll come back to that again. But if you just look at that, and you plot that out, what you get is, if you plot out, a cosine and plot out a sine, what does the correlation mean? The correlation just means the dot product, which means imagine you turn that cosine into a vector, and each value of the cosine is another element in the vector. And so then we just do the dot product between all those elements, like that, multiply them all. And if we do that, the answer is 0. So they're completely uncorrelated with each other. But that's also true, so this guy equals 0. But that's also true, the correlation of, the cosine of one frequency and the cosine of another frequency also equals 0. And so that implies that the correlation between any sine of any one frequency and a cosine of any other frequency is also going to be 0. So basically, we're decomposing into these principal components that extend across the whole time or the whole image, and they're all perpendicular to each other. They're all translated means they're all uncorrelated with each other. Translated, they're all orthogonal to each other at right angles to each other. Translated, the dot product between them, if you think of a cosine as basically just a long vector of coordinates, the dot product between them is 0. So those things are all the same. And it's worthwhile just doing it in MATLAB just to see. Or just do something like, say, take a sine with one hump in it, and then just take a sine with two humps in it. And magically, the correlation between these guys is also completely 0. When you multiply those out, you get 0. Okay, so it's sort of counterintuitive. You wouldn't when you look at it, just eyeball, it doesn't look like that would always be the case for all those curves. But that's that's the case. So now let's just write out the Fourier transform again and directly convert it into space, so we can see what the what space is, what space corresponds to. So, and usually instead of frequency, so here's our original Fourier transform. So the Fourier transform at a particular frequency is just equal to the sum over all time of the non-Fourier transform signal at a particular time point. So there's t here and f here, times e to the minus I 2 pi frequency times time, summed over all little fragments of time. So that was the original. So here's our time signal, and we turned that into a frequency signal, same number of numbers in it. And so when we change over to the spatial Fourier transform, we usually use k instead, so that's why it's kSpace. So it's kSpace just because we're going to use that to sort of indicate space instead of time. And so everything else is pretty much exactly the same, and notice this is just a 1D, so this is 1D ft. 1D FTs. So here we go to x instead of t, and so frequency goes to k. T goes to x, and then if we have our function h as a function of x times e to the minus I 2 pi k, because k is frequency, times x, summed across every little bit of space. So t goes to x, so here's another t going to x, and frequency goes to k, and that guy goes to. So this is our spatial Fourier transform. So it's exactly the same as the temporal Fourier transform, but it just has space in it instead of time. And so that means it's still called frequency space, but it's spatial frequency space instead of, so kSpace is spatial frequency space instead of temporal frequency space, like it would be in the case of an audio signal. So this side, we call this the frequency domain. And this side, sort of this guy is not the frequency domain. So not the frequency domain. And so on this side we have temporal frequency. So we have temporal frequency, which goes back and forth with time, and then spatial frequency, which goes back and forth with space. So just make sure we get all the the analogies correct. So here's space. So x. So what we want to do now is, without writing out the equation for a 2D Fourier transform, basically all it has is it has some addition in the exponent. That's all there is to it, pretty much. I'm just going to sort of write out the spatial domain, the image domain, and it's a little confusing because I'm going to put the image domain on the left. So here the image domain is on the right side of the equation, and the frequency domain is on the spatial frequency domain is on the left side. I'm going to flip that around here, so I'll put the image domain on the left. So that's the small letter on the left. And what we want to do is, there's many different ways of representing the data. And so we're going to look at 10. So the idea is you have to allocate memory space for 10 different representations, and don't get them mixed up. So some of them are redundant. They're sort of referring to the same thing, just looked at from a different point of view. But there's 10 different sort of ways of looking at the same thing. And then each of these 10 things has 2 dimensions to it. So that's like we're going to do x and y just for a 2-dimensional Fourier transform. So we'll start off. Here's the image domain. So that's not frequency. And then here's the spatial frequency, kSpace, spatial frequency. So the ones that are in the vertical line are all basically equivalent to each other. But I just want to write them all out. So because you'll actually manipulate them when you do the Fourier homework, you can see that you have to go back and forth between the Cartesian and polar coordinates. So first we have the real image. So let's imagine we got a brain there. Okay, there's a brain. So this one is real image. Now you might wonder what other kind of images are possible, and the other kind of image that's possible is imaginary image. So here's imaginary image. And what's imaginary image? It's all 0. So in the best of all possible worlds, it's all 0, but it turns out it's often not 0. We'll find out about that. So imaginary image. And we have a way of converting to polar coordinates, which we often use, and that method is just, we just have a real and imaginary here, and then we can sort of convert that into, here's the real and the imaginary, we can convert that into an angle and an amplitude. So if we do that, we then get another way of representing this image. And in this case, it would still look like a brain, but this would now be the amplitude image. So this one's particularly simple. It's not like this in real life, but if everything was perfect and the imaginary part of the image was all 0, the amplitude image would look just like the real image. Because if there's no y component of the complex number, then it's just the length of the vector along the x-axis, and that's the same as the real value. So the real value and the length of the vector along the x-axis is the same. And then what would happen for the other component? This other component would be the phase image. There's the phase image. And the phase image would be all 0. If this was a positive, the real image was all positive, this guy would be 0. There might be some 180s in there if it was negative, if some part of the image was negative. But if it was a positive real image, you'd end up with 0. Now, there's another way of looking at that, which is kind of the way that like a mathematician would sort of mentally have. It's not usually drawn out this way, but you could also just look at the actual vectors. So imagine you've got, all these vectors. So here's vectors, and they're different lengths because there's different brightnesses in the image. But you basically you'd have a brain filled up with a bunch of vectors, and their phase angle would all be 0. So it's all pointing toward the along the the x-axis. And then there'll be some tiny little vectors out here. So these guys are tiny. So tiny vectors out here. So that's mostly black out there. Still be a vector, but a very tiny one. So these are 5 different ways of thinking of the same data. We can either draw the vectors out, we can draw the vectors out in Cartesian coordinates, or we can draw the vectors out in polar coordinates. We can decompose the vectors into 2 things. So the Fourier transform operates on the Cartesian coordinates, but usually when you want to look at it, you have to do this conversion, and there's functions in MATLAB to do that conversion sort of automatically for you. So these are, this is our complex vectors. So these are, in some sense, this is like the most basic way of thinking about it. But now, don't forget, we've also got sort of like, 2 additional things. We got x and y going here. So, here's x. All these guys have x and y. So we don't want to get those mixed up with, the real and imaginary, which are also kind of like x and y. And I've often got these. There's x and y on this too. Okay, so that's our. So we've allocated memory space. We've got 10. We've got 5 things allocated, each of which has an x and y in it. So now we can Fourier transform this. And so if we Fourier transform this, Fourier transform can go, back and forth. So we do the Fourier transform that way. If we want to go back, then we just do the inverse Fourier transform, which is the same as the forward Fourier transform, but just with a sign difference. And so if we Fourier transform that, what do we get? So we get k-space. And so what is k-space? So here's k-space. And so we first have the real spatial frequency component, and then we have the imaginary spatial frequency component. And what does this look like? This typically, it comes out of the Fourier transform with the 0 off to one side, but there's a function sort of IFFT shift, or FFT shift, to put the 0 in the center. That's a MATLAB function. The reason it comes off on the side just has to do with how the Fourier transform is implemented. So it's kind of like it's just sort of an accident, and you could sort of think of it as an accident in a way. But let's put this spatial frequency 0 in the middle, and we'll talk about that next time. What is the center of k-space? The center of k-space is just the average brightness of the image. We'll explain why that is. Center of k-space is very important for determining what the image looks like. It's by far the thing that affects the way the image looks the most. And then what we've got are the coordinates of k-space. So spatial frequency, this is k-space here. So then we have the coordinates. And what are the coordinates? The coordinates are sort of the kx coordinate and the ky coordinate. So that's the spatial frequency coordinate in the x direction and the spatial frequency coordinate in the y direction. And you could have points in here that have components of both. So if you have a point that's up here, what that means is, so again, we're sort of decomposing. So we decompose that into a particular kx here and a particular ky here. So, that point contains a certain amount of y spatial frequency and a certain amount of x spatial frequency. So we'll go through in more detail how those sort of interact with each other. They kind of don't interact with each other, so they can sort of be manipulated independently. But that's yet another x and a y. So it's kind of the x and the y coordinates of k-space. So what is the actual And then at each point here, we've got a number. And so what do those numbers actually look like? They don't look like a brain. They look like there's a whole bunch of large numbers right in the middle. And then as you sort of head off to the side, out into higher spatial frequencies. So let me just put this, draw this better. So there's a 0 there. So this is, K, Y going positive, and here's negative KY going that way, and same with X. So this is, KX positive, that's, negative KX. So it turns out, if you look at this, and the same thing occurs over here. So there's very large numbers in the middle, and then there's just much smaller numbers off to the side. And so why is that? It turns out if you do a Fourier transform of just about any natural image that's not something like carpet. So if I look down at the carpet and do a Fourier transform of the carpet, it's very uniform looking kind of thing with no objects in it. That won't look like this. The Fourier transform of a carpet wouldn't look like that. But the Fourier transform of natural objects, sort of objects out in the world, typical objects in the world, always looks like that, has a big peak in the middle. And why is that? So we'll talk about this, multiple times, but one of the reasons, let's just sort of go back to the way we were thinking of a Fourier transform as a correlation. So imagine we've got a brain image over here. So here's a brain image. What spatial frequency does that correlate with the most? I always ask this question. What spatial is it? Spatial frequency 7, spatial frequency 35, spatial frequency 4? It turns out there's one very clear answer. What does that correlate with the most? And so let's just do this in one dimension. So let's just go across the brain like that and plot that out. And what do we get if we just plot that out as a one-dimensional thing? We get sort of not brain, and then brain starts, and then not brain. So this is X here. And what's this? This is brightness. So now the question is, what does that correlate with? What spatial frequency does that correlate with? And it turns out it correlates with spatial frequency 1. So spatial frequency 1 is by far the largest number in the Fourier transform. And so what is spatial frequency 1? So, well, let's take a cosine. So here's a cosine like this. That actually kind of looks like that. So a cosine is, it looks like a negative cosine, right? So that's what I drew there in red was the positive cosine. And so if we correlated this, and what does that mean? Like multiply all these guys times each other, and these guys times each other, these guys times each other. What you would get, you'd get a big negative number. Large neg. You get a big negative number. It's negatively correlated with a cosine. Or you could say it's positively correlated with the negative cosine. That by far is the biggest correlation. So what about, but you might think, well, what about there's a little sulcus over here. There's a little sulcus, and it's dark in the sulcus, and it's light over here, and it's light on that side. That turns out to correlate with a higher frequency cosine. So so here's a higher frequency, higher spatial frequency, and that little bit, maybe just this little chunk of it right here might actually correlate with, light, dark, light across the central sulcus. Now it's certainly not going to correlate very well out here in the black part because that's all flat. And so that number, will be out in k-space, and so that one won't actually correlate. That'll be one of these very small numbers here, way out in the high frequency part of So basically, any of these directions are going, to high spatial frequency. So way out in the periphery of k-space, we're going to have high spatial frequencies. There's going to be some correlation, but it's not going to be very big. And by far the biggest one will be 1, because the brain looks like a cosine. It doesn't look much like a sine. So the correlation with a sine is not going to be very good. So here's I'll just put a sine of 1 in there. Doesn't correlate with that very well. It really correlates, it looks like a negative cosine. So that means it's negatively correlated with a large negative correlation with a cosine. Okay, so we rarely look at this, at the real and imaginary spatial frequency. We almost always look at the amplitude of the spatial frequency and the phase of the spatial frequency. And what does that look like? Well, the amplitude of the spatial frequency looks just like the, either the real or the imaginary spatial frequency. But the phase of the spatial frequency is the phase angle, and that's going to vary between 0 and 360. And that just looks like just this complete random picture. It just has to do with exactly where stuff is in the, where stuff is. So imagine we'll talk about this again, but imagine we push the brain off to one side. What's that going to do? It's going to make it correlate with the sine a little bit and correlate with the cosine a little less. And so then that translated means it's going to have a different phase angle. So this is the phase picture. And then last but not least, to round out our 10 different allocated memories, we're going to have the picture with arrows. And so what does that look like? Well, there'll be some big arrows in the middle, and they're pointing in various different directions because they've all got different phases. And then as you go out, there'll be like little tiny arrows out here, tiny vectors out here as you go further out. So that's the, in some respects, this is the most basic one. It's a bunch of little vectors at each xy point, kx, ky point. So remember, this is k, kx, and ky. Okay, so that's our start. So what do you see on the screen? You just see one of these on the screen. So this is the one. This is what you see on the screen. So that's the one that you see on the MRI screen. You don't see this one. You just see the amplitude image. Okay, so that's just our intro to k-space to spatial frequency. And so what we want to do now over the second half of today and tomorrow is to go over some very simple Fourier transforms. What do they actually look like? So just plot out take something on the left side and then plot it out on the right side. Once we've Fourier transformed it, what does it look like? And then just sort of see how things change when we change very simple images. And so just to make things, since we already argued that it kind of looks like a cosine, let's just assume for the purpose of a very simple, so what we're working up to is what is one point in k-space, because it turns out 1 point in k-space is it's more complicated than 2 points in k-space. So what is 1 point in k-space? It took me years to really sort of finally understand what the real meaning of 1 point in k-space is. So that's what we're working at the end of tomorrow. We're working up to 1 point in k-space, but we're going to start off with a simpler case, which is, imagine we have a cosine brane. So imagine our brain is just a cosine. So, it isn't a cosine, but we can sort of start off with that. So let's, so we look at, here's our, real image. Oops. Yeah. So this is the case of a real only image. Okay, so I don't mean like the real component, but I'm just mean if we have something like a brain that doesn't have an imaginary component to the image, it just has a real component to the complex number of the image. So here's our real image, and for our real image, here's the image. We're going to use a very simple cosine brane. So the image at an xy point is just equal to the cosine of x. So what does that mean? That means like you can change y. So as you sort of fill in your image. So here's our image. So I'll draw the 4 parts of the 5 parts. So if you look in the notes, I'm sort of using marker to mean dark. So the notes are sort of shaded light to dark, and so it's just so that when you go back to the notes, it sort of looks like the same thing. This stands for dark, and this stands for 0. So this guy is the real image, so it's a real only, and this guy is the imaginary image, and there's no imaginary, and it's just a cosine. So if I plot it out underneath it right here, it's just a cosine like this. So that's 1 and minus 1, and this guy is just 0. So what if we convert that? So this illustrates some of the practical problems. What if we convert that to amplitude and phase? So this guy, so now we're doing the second. So here's amplitude and phase. So what does that look like? It's slightly weird. So amplitude is just, if it's just a cosine, then the amplitude is just the height of the cosine, but it's the absolute value, so this guy goes up again. So if you plot that out, what does it look like? Well, so it's 0 over here, and 0 over here, and so and then it sort of goes up like that, and it goes up like that. So you end up with something that's slightly weird, because we took effectively, when we get the distance, we take the absolute value of it. And so what's going to happen, there'll be sort of some dark spots here. These are practical things that you'll run into if you actually just do a Fourier transform of a simple function. So what does the phase look like? Well, the phase angle is also going to be kind of weird. So what's going to happen to the phase angle is, if you think about it, you're going to end up with sort of 180 here and 0 here. So if you just do this, just work that out, just do this kind of thing where you have a real and an imaginary, and then you have an angle and a, not big enough. Try that again. So, if you've got real and imaginary and phase angle and amplitude, you'll end up with a little flip there when you go into the negative. It's because when you're going into the when you're going into the negative here, that has to be flipped over to 180 degrees instead of 0 degrees. Yeah, in the middle. Yeah, so so this part in the middle here corresponds to 180 degrees because you're in the negative. The vector is pointing in the negative direction. So that's slightly weird, but that's just the way it is. And we can also look at that as a bunch of arrows. And so the arrows will be biggest here, and then they'll get smaller, and then in the middle they'll be pointing that way, and then they'll sort of get smaller again, and then in the side they'll be pointing that way. So there'll be a bunch of arrows like that, and right down the middle of the image they'll be pointing at 180 degrees. So it's worthwhile just sort of going through all the different things to make sure that we have a real complete understanding of what the mapping is between real and imaginary, amplitude and phase, and vectors. So now let's do the Fourier transform of that. And so when we do the Fourier transform of that, so ft, what do we get? So here's the first slightly weird thing. So we get 2 points over here. So here's the Fourier transform like that. So the average brightness of this image will be, of our cosine brane, will be 0, because the average, I didn't draw this quite, this guy is a little bigger, and it goes up like that. There we go, it's a better cosine. So the average will be 0, so the center of k-space is 0, but then there'll be basically just 2 points in k-space at frequency 1. So this will be, that's frequency -1, and that's frequency 1. And everything will be 0 over here, because it doesn't correlate with a sine at all, because it's a pure cosine. So that's what it is. And so what are those points? These points are, this guy is, kx equals -1, ky equals 0. That's what that point is. So, and if we convert that to polar angle, it looks the same. We just end up with 2 numbers there like that, 2 positive numbers, and this is all 0. It's all 0 everywhere else. And if we convert that to arrows, what does it look like? It just looks like 2 little arrows. There's one arrow pointing along the 0 phase direction, and another arrow pointing along the 0 phase direction. So that's vectors. And so this is the k-space version. So this is, real k-space, imaginary k-space, amplitude k-space, phase k-space, vector k-space. So this is, we're in the Fourier transform of real only image. So now the first thing that comes up is, why do you have 2 of these guys? So what is a negative frequency? So why do you need a negative frequency? So you have like this. So this is, this is positive frequencies over here. This is positive y frequencies and positive x frequencies. This is negative x frequencies, but still positive y frequencies. So why do you need 2? So I'll go over this again on Friday, but the reason you need 2 is we need to stamp out the sign, because we only want a cosine. So if you think of 2 spots in k-space, remember you can think of the inverse Fourier transform as a correlation, just the same as you can think of the forward Fourier transform as a correlation. And so how do we get a cosine over here? Well, we need 2 spots, and you can think of 2 spots as picking out, so here's our cosine, like that, going across 0. So how do we sort of pick out a cosine? Well, we need to sort of pick out two positive points that are the same distance away. So that will correlate with, those two spots will correlate with a cosine. That will correlate with a cosine. And so we need two, unfortunately. And the way you pick out a sine is you make one of them negative, because a sine is an odd function. And so if you go out the same distance in the two directions, you'll end up with the opposite thing instead of the same thing. So that's kind of the reason we need two. We'll come back to that. That's sort of a difficult one to digest. So now let's start messing around. So we've done the absolute simplest possible. So you can do this in MATLAB. You can just take a cosine. You can just define a function as the cosine of x, take the Fourier transform of it, and just look at it. You get two little spikes across 0. That will be one of the homework assignments. So now let's start messing around with it. And so the very first thing we could do is, what if we just add something to our image? So let's make our image, let's shift it a little bit. So if we shift the image a little bit, so make our image equal to the cosine of x, but subtract off 45 degrees. So this is, that's 45 degrees, pi over 4. So what does that do? That just shifts our image to the right a little bit. So when we subtract off, it sort of goes the opposite way because we subtracted off our argument. So if you plot that out, so this is our cosine brane with a 45 degree shift in the cosine. So what does that look like if we plot it out this way? Well, it's pretty much the same as it was before. It just shifts it over a little bit. So what will happen is it will just shift it a little bit. It won't shift it all the way to a sine. So let's just draw sort of a cosine here and draw a sine here. It'll shift it about half of the way to a, it's going to shift it half of the way to a, so it's about like that, something like that. Just move it over to the right a little bit. And so if you just draw that out as kind of a brightness, it'll be darkest right here where it's negative. And then it will start to sort of shade off a little bit in these different directions. So all you did is you just shifted the guy that way a little bit by 45 degrees. So just moved it over a little bit. And if everything else is the same over here, so this is still going to be all 0 over here for the imaginary part because we still have just a real image. And then if we look at the amplitude and the phase, they're going to be a little, a little messy. So what will happen is it'll look like this, but it'll sort of be shifted over a little bit. So it's going to, it'll be partly shifted over. So it's going to go like that, something like that, because it kind of got shifted. The main hump got shifted that way. This is still all going to be 0. And then, what is the arrow is going to look like? They're just going to be shifted over a little bit. So there'll be, oh no, sorry, this guy isn't 0. Right, so this one is a little weird because it's going to have two humps in it, like that. And then this little phase picture is going to be shifted over. It'll look something like this. Like here's the dark parts of it. So all we did is we just shifted that guy over and wrapped around to fill in over here. And then finally, what about the arrows? The arrows will just be shifted over. So the biggest arrow will be here like that, and then the biggest left arrow will be here, something like that. So it'll just sort of shift this arrow pattern just over to the right. Okay, so now what happens when we take the Fourier transform of that? So when we take the Fourier transform of that, interesting thing happens. So this is, this is real on the image. And FT. ft of it. So what's going to happen now is we're going to have 2 points here for the real image, but we're going to also have 2 points here for the imaginary one. So this is, so here was the real image, imaginary image, amplitude image, phase image, vector image. And now we're in spatial frequency space, k-space. And so here's the real spatial frequency representation, the imaginary spatial frequency representation. So you're going to end up with both. Now, why is that? Well, it's going to be because we're basically correlating with cosines and sines. And so this says it correlates somewhat with the sine as well as a cosine. And those numbers will be slightly smaller because, as we rotate, so if we were perfectly correlated with the sine of a cosine, it's going to be like that. But as we start to move up, these two numbers, the real and imaginary part, will get a little less than they would have started. This number is going to be a little smaller. So both of those numbers will be a little smaller, but there'll be some numbers appearing in the imaginary part of k-space as well. And if we convert them to amplitude and phase, we're going to see the same thing. So there'll be 2 here, and then the phase will no longer be 0. But it will be not 0 in an interesting way, which we can only see easily if we plot it out. So if we plot it out as arrows, what happens is we've rotated the phase of our vector picture. So, which we can see here, because these used to be, if you look over here, these used to be 0, and now there's a number. The phase was all 0 in this case. Now the phase it's got actual non-zero parts to it. And what are the non-zero parts? Well, it rotates this guy 45 degrees, and it rotates the negative frequency part negative 45 degrees. And so this is the first of many very hard to remember things. So bizarrely, what happens is when we mess with the phase in k-space, so what do we mess with it? It used to be like this, and now it's like this. So we didn't change the location in spatial frequency space. We just changed the phase. So we keep the amplitude the same and just change the phase. What does it do? It shifts the image. It actually shifted the image over this way. Or, vice versa. We shifted the image, looked at the Fourier transform, and found what happened. It messed with the phase. It didn't change the actual distribution of spatial frequencies at all. It just made the phase. And we'll come back to this and talk about this as, you call this the Fourier shift theorem. We can write it out in mathematics, but hopefully you can sort of see what happened. So we just moved the cosine off to the side, and when we did the Fourier transform, it just messed with the phase. So a phase shift in an angle of the complex number in k-space equals an actual spatial shift in real space, in sort of non-frequency space. Okay, so we're fighting our way up to an actual single point in k-space, because that's what all the data is. All our data is collected as single points in k-space. And so we haven't got there yet, because this is 2 points. So a cosine is actually 2 points, like sort of our cosine brain. This is our cosine brain. So a cosine, just a blob, a basic blob, is actually 2 points in k-space. So what is 1 point in k-space? It turns out it's got some phase in it. It's got some complex numbers in it. And so we'll get to that at the end of tomorrow. But before I completely overrun, David, let's end the recording now just in time, and I'll ask for some questions.